Hello. So, in this video, we're going to be discussing whether or not derivatives exist. So, this is one of those things, sort of important but easy to overlook bits, is sort of determining whether or not a derivative actually exists at a point before going through all the effort of actually computing it. But like most everything with derivatives, this all comes down to the fact that the derivative is actually just a limit in disguise. Okay? So, in particular, we want to know when a derivative is defined, which is sort of the same thing as saying when it exists. So if you can sort of interchange those two when you see it or read it in a text, these kinds of things. But what we actually mean when we say that is whether or not the limit exists, specifically not the limit of the function, but the limit of that difference quotient, right? The actual definition of the derivative itself. So, a good way to think about whether or not that derivative exists, whether or not that difference quotient is sort of defined, because it's hard to sort of look at a graph and think difference quotient version of that graph, right? So, a good way of thinking about it is to look at what's happening with the rate of change, right? Remember, the derivative is supposed to represent this sort of rate of change of the graph. So, let's sort of look at a quick example for sort of our first bit. So here, if we wanted to know, does the derivative exist at x equals 0? So we would go to where x is 0. So that's, right here at the y-axis. And we'd want a line that is tangent at that point, right? So with a little bit of effort, we could indeed make a tangent line at that point. But what if we wanted, for example, x equals 1, right? So x equals 1, that's going to be sort of this missing part here, right? This vertical tangent line, that's at x equals 1. And so there's no real way to make something tangent there, right? And this is sort of an obvious but important thing to make note of, which is like, first of all, in order for the derivative to exist, we need the function to exist, right? It's hard to be tangent to a graph when the graph isn't there. So first bit, we need the graph to, have that point on there so that we can actually be tangent. Unsurprisingly, that's not maybe quite enough. So again, let's take a look at another graph here. So again, we're looking at x equals 0, and we have right here, right, the x equals 0 line, and we indeed have that one point, right, where it actually is defined there. So the good news is we can make a tangent line through there, right? So here is an example. We have a tangent line. The problem is that we can make more than one tangent line, right? And this is not ideal. So like this line is tangent, but so is this line, and that line, and that line, right? So when we are talking about sort of the derivative, the idea is to have the slope of the tangent line, and now we're like, okay, but which one, right? That's not great. We want our derivative to be a function, which means we want it to have one output. We want one answer when we ask these questions. So what's going wrong here, right? So maybe pause the video for a second here, see if you can figure out why we are able to make all of these tangent lines instead of only having the one. So I'll give you a second here to think about it. All right, so hopefully you paused or have a thought here, but what it comes down to is that we have this sort of gap, right? So this gap allows us to sort of pass through that section in a way that we could sort of do a bunch of different angles and still not intersect the graph in another spot. So this is a problem. So in order for the derivative to exist, yeah, we need the function to exist, but that's clearly not enough. What we need is that we don't have a gap like that. But remember, this is one of those types of discontinuity that occurs when the limit fails to exist. So another thing we could sort of add on, our second observation, we need, in order for the derivative to exist, the limit of the function to exist, right? So we've been talking about the limit of the difference quotient. That's sort of what we're after, but it turns out we also need the limit of the function to exist. But hopefully at this point, some sort of like weird, warning is going off in your head, or maybe some, harkening back to some other stuff we've done. If we need the function to exist and we need the limit to exist, and clearly these things need to be the same thing, right? Otherwise, like, we would have a point off in space and still be able to go through it a bunch of different ways. That's actually equivalent to needing these things to be continuous, right? So when we are looking at these two sort of observations, although we came at them sort of separately, they're sort of culminating in this nice mathematical idea we already have, which we can use to replace those first two things, specifically that in order for a function to be differentiable, then we need the function to be continuous. But again, this is sort of always a good thing to ask, is that sufficient, right? So like, it's true that if I'm going to be differentiable, if the derivative is going to exist, I need to be continuous. But are all continuous things differentiable? Are all continuous things mean that the derivative exists? And sadly, of course, not so much. So let's look at an example here. So we have this function, which may look, again, somewhat familiar. This is very similar to an absolute value function. And let's say we want to look at this part where x is -1, right at this little vertex part. So again, we want a tangent line. So we can make a line that goes tangent to the graph, right? Only touches the graph in one spot and goes through that one corner, that one sort of point on the end there. But that one does too, and of course, this one, lots and lots of others, right? So we still have this problem where we have more than one possibility. So this is one of the examples of the two types of situations where you can have a continuous function that is not differentiable, right? So not differentiable meaning that the function, the point the point of the function doesn't have a derivative, right? And this is an important distinction because there are points on this where it is differentiable. So being non-differentiable means it's at a point, a specific spot. So this is not non-differentiable point specifically at that x equals -1, okay? This thing is also cleverly called a corner because it looks like a corner. Math people, kind of lazy with the naming, we try to keep it pretty obvious. So what's happening here is that you have sort of one slope and a different slope, right, coming into that same spot. And so we have no transition. There's no sort of smooth curve between the two. They just meet in this sharp point, okay? This is a corner. The other version of this is in some sense the same thing. It just is visually a little different, and mathematically it has some slightly different properties, so we give it a different name. And this thing is called a cusps. So they still meet in this sharp point, but now instead of coming in straight, it comes in sort of in a curve, right? So it is curved as it meets rather than straight as it meets. Okay. So what do we do? So we can determine that a function must be continuous at a point if there's sort of any hope that the derivative is going to exist. But it's still possible to be continuous at a point and still not be differentiable at that point. So in particular, we have these corners and cusps, right? So it's not quite enough that you are continuous. You need to check a little bit more. Nonetheless, continuity at the point is necessary, right? So we know we have to have at least that. It's just not sufficient. So it's possible to be non-differentiable despite being continuous. So that is sort of the sum of all of the continuity and differentiability, right? This idea of being non-differentiable, it needs continuity to be differentiable, but there's more to it. And that's sort of the important thing to take away here. And keep in mind too, that we're going to be going both directions with that. If we know something is differentiable, that means it must be continuous. This is also a useful thing to keep track of and something we'll use in the future. Okay. So that's that.